Hello everyone and welcome to today's Osmine Geofabrics webinar. I'm Ross Carter. I'm the Membership Manager for Osmine here in New South Wales and I'm pleased to be your host today. Before we begin, I would like to acknowledge I'm hosting this webinar from the lands of the Awabakal people on the shores of Lake Macquarie. I also acknowledge the traditional custodians of the various lands on which you all work today and the Aboriginal and Torres Strait Islanders people attending this webinar. Today's webinar is titled Geosynthetics and ESG Compliance in Mining and brought to us by Geofabrics. Today I'm joined by Ryan Hackney, Environmental Solutions Manager of Geofabrics. We're very fortunate today to be joined by a true master of the field of geosynthetics. Ryan is passionate about the role geosynthetics plays in the protection of the environment, supported from over 16 years of geosynthetic testing, analysis, development, and applications expertise. Geosynthetic construction materials can be used as an economical and sustainable alternative to traditional construction methods. Ryan has a bachelor's degree in geological sciences and master's in engineering geology. He's past secretary and current treasurer of the Australian chapter of the International Geosynthetic Society. I personally look forward to today's presentation for two reasons. This is great because it's an example of ESG in action in our day-to-day activities, not being treated as something else. And secondly, Geofabrics as a fine Australian company supporting Australian manufacturing and jobs. So, like I say, for me, it's a bit of a double whammy. Today, Ryan will explain to us how geosynthetic engineered solutions present opportunity for operational activities throughout the life of mine to deliver better environmental outcomes. Following Ryan's presentation, there'll be opportunity for Q&A, and please use the Q&A button at the bottom of the screen to send through your questions at any time. You can also upvote on other audience questions. So without further ado, I'll hand over to Ryan Hackney for this presentation. Welcome, Ryan.
Thank you very much, Ross. And welcome everybody, and thank you for joining me today. So as Ross highlighted, today I'm going to be talking about geosynthetics and ESG compliance in mining. My name is Ryan Hackney and I'm the Environmental Solutions Manager at Geofabrics Australasia. Just to get started, a definition of a geosynthetic material. So for those in the audience that are not wholly familiar with geosynthetics, I've got a few brief slides that are going to introduce geosynthetics and the functions. So to start with, a geosynthetic, it's a generic term and it describes a product, at least one of whose components is made from a synthetic or natural polymer. Geosynthetic materials, they're usually in the form of a sheet, a strip, or a three-dimensional structure, and they're used in contact with soil or other materials, mainly in geotechnical and civil engineering applications. So there are a number of geosynthetic types, and this table outlines some of those geosynthetic types. There are more types than this, but I would say that these broadly cover the majority of the geosynthetics that we see in use on mine sites. So these include geotextiles, geosynthetic barriers, geogrids, geocomposites, geonets, geosynthetic clay barriers, geocells, and geomats. So the term geotextile and geogrid, material, it was probably first established in the late 1970s. And these material types, there's subgroups that can be associated with these types as well. So geotextiles we can break down into wovens and non-wovens, and then further to that is further manufacturing methods that can produce different types of geotextiles, and the same can be said for a geosynthetic barrier as well. So there are many different geosynthetic barrier types. We can look further into that in a few slides time, but again, we can have polymeric geosynthetic barriers, we can have bituminous geosynthetic barriers, and we can have clay geosynthetic barriers or geosynthetic clay liners, but they are associated with their own type there as clay geosynthetic barrier. So the different geotextile types all serve either one or a number of different functions when they're utilized in an application. So this matrix just displays the different geosynthetic types and the associated functions that they can perform. So we start with a barrier function. So a barrier function will prevent the migration of a liquid or a gas from one area to another, and it's essentially a impermeable layer to prevent that migration of fluid or gas. We have a drainage function. So in situations where we want to convey liquid or gas from one area to another. So an example could be on the back of a retaining wall where we want to relieve pore water pressure acting on that wall. We can use a drainage geosynthetic to capture that water and disperse that into a drain, or in a capping application where we want to capture infiltrating water and drain that to a specific area away from the site. We can use drainage geosynthetic to serve that function. Filtration. So filtration is an application where we want to utilize a geosynthetic, and it's usually a geotextile, to establish a soil filter. So essentially the geotextiles, rather than being classed as a filter themselves, they actually are used as a catalyst to form a natural soil filter. So geotextiles have pore openings and pore spaces, and what happens in the filtration process is the larger soil particles will bridge pore sizes within the geotextile themselves, and then smaller soil particles will then create that natural soil filter behind the larger particles to establish that natural filter system that's been catalyzed by a geotextile. Another function is a protection function. So again, we can use geosynthetics to protect either part of an asset or typically protect another geosynthetic type. So a good example of that is where we use a geomembrane to serve a barrier function. Essentially, we want to protect that barrier from either installation damage or long-term damage, and we can use a protection geotextile to serve that function. So it's a heavier mass geotextile that cushions against materials that are placed on a lining system. Next up, we have reinforcement. So there's numerous examples of the reinforcement application. One could be the reinforcement of a soil to increase slope angles. So we can build steeper and steeper slopes by reinforcing the earth with geosynthetic types, and that could be a geogrid or it could even be a certain type of geotextile that can form that function. Further to that, we can reinforce subgrade soils to allow construction on poorer quality soils, so low CBR subgrades, for example. We can use reinforcement geotextiles or geogrids to allow construction on this less suitable subgrade material. Similarly, we've got stabilisation as well. So stabilisation that incorporates geosynthetic types of geogrid and geocells, and stabilisation is a function whereby we stabilize the ground by using these type of stabilization geosynthetics, and they lock in granular materials. They prevent lateral spread, and hence we can improve bearing capacity, for example, on weaker subgrades by using stabilization geosynthetics. Separation is a function whereby we would want to separate two dissimilar materials. So one example could be in an area where we have a clay material and then a more sandy material, and we don't want those two soil types to intermix. So to prevent that intermixing, again, we can use a geotextile to serve that separation function that forms a physical layer between the two and prevents that intermixing occurring. And finally, on this table, we've got erosion control. So we can use geosynthetics, and again, a certain type of geotextile that can prevent or assist in erosion control. And I've got some examples that I'll show that show this. So I've just got a few photos just to display geosynthetics in action in some of their applications. Here you can see a pond that's been constructed you can see that here in the pond you have initially a prepared subgrade. So you've got essentially a low sloped base that would run to a sump, and then you have these batters that have all been prepared with a certain soil type that's been conditioned and compacted to achieve optimum conditions for the geosynthetics to then be placed. They're usually rolled smooth so that they can accept these geosynthetic materials without inflicting damage on them. In the base here, you can see a modified geosynthetic clay liner that's been deployed as the secondary barrier in this system. So you can see that these panels are laid out along the base. You see these creamier sections. This is typically a 300mm overlap, and by overlapping these panels, that creates the hydraulic seal between each panel. So we want the barrier to perform normal to the plane as well as it does through the joint as well. And then on the slopes here is an example here of the this white material here. This is a white geomembrane, and underneath this white geomembrane you will have this geosynthetic clay liner as well. So this is just in progression of construction. It gives you an example of the various elements in the construction phase. Here we've got a high strength woven geotextile that's used. So these are typically used. This is an RSI, Solmax RSI woven geotextile, and these are used for reinforcement. They have high tensile strength at low strains, and they're used to reinforce the ground. So applications where you've got maybe a poorer or a soft subgrade, and you want to improve the strength of the ground, create a working platform or a road or a rail. You then place angular material onto this. It's got a high level of installation damage, and it allows for reinforcing that weaker subgrade to be able to then construct or traffic along those layers. Here we've got an example of geotubes. So geotubes are this is a woven type geotextile construction. These are factory fabricated, essentially really large pillowcases, and these tubes, these geotubes, they can then be pumped with mine waste and sludge and slurries. And essentially the idea is that we pump these full of slurries and sludges, and the pore space, the geotextile pores in this woven construction, they allow the water to escape quickly out of the pores, but at the same time they need to retain the solids within the tubes. And by flocculating or adding polymer to the sludges, we can control the particle size or create a large blocked particle that doesn't escape through those geotextile pores, but at the same time allows that rapid dewatering, so the water can escape and the solids stay within the tube. Here we've got an example of a waste containment cell, and again it just shows various geosynthetics within the system. So here you can see this is a sump at the base of the cell, and you've got the geomembrane, this black material that's serving that barrier function. So it's preventing the liquid that's within this sump penetrating into the surrounding ground and essentially contaminating the surrounding water table. And then above this geotextile, you typically use a cushioning geotextile. So the cushioning geotextile providing that protection function. So you can see this grey material that's sitting and placed on top of the geomembrane. This is placed on top so that then we can place this layer of drainage aggregate on top of the geotextile. So typically in this landfill cell, you would have about 300mm of aggregate that sits on top of this lining system. And you can see once you've placed this aggregate on top of the lining system, it can then be trafficked with plant to aid construction and carrying construction. So you typically wouldn't traffic on geosynthetic materials with this type of heavy plant that could inflict damage, put holes in the lining system, and essentially render an impermeable liner a lot more permeable due to holes that could be inflicted in there. So once the geosynthetic materials have a level of other material placed on them, it allows for a bit of trafficking during construction. Talking about holes and this impermeable liner, there are holes that can be made during the construction process. So there is something called leak detection surveys that can be carried out either on an exposed membrane once it's been installed, or once we've placed this cover layer of drainage material, we can use a dipole method to assess this liner to ensure that during construction we've got a low level of holes and imperfections that can be remediated before the construction of the site is signed off. Here again, we've just got an image of a waste cell that's being constructed. Here you can see that the geomembrane is being deployed in the cell, and there's a geotextile that's been placed on top of it here. In the foreground, you can see these two ponds. So these could end up being leachate collection ponds, because there's this. Once this cell has been constructed and this waste being placed in it, obviously you get infiltration from rainwater, and that can interact with the waste and generate a leachate. So the leachate can then be collected at a sump, like we saw in the previous photo, and that leachate can be then diverted to a leachate pond to either evaporate or be treated at a later stage. So it's likely that these type of ponds will also be a lined system once the construction phase gets here. So again, this will have a geosynthetic barrier system installed to prevent this leachate penetrating into the ground. This is an example of a cap. So once a waste cell has been filled, we want to cap the system so that we no longer generate any leachate, and the waste and the site can be remediated. So this cap here, we can see on the right, there's a geomembrane that's been placed over the waste body. So the geomembrane prevents water infiltration getting into the waste body and allowing leachate to continue to generate. So by capping the site and capping the waste off, we cut off that leachate generation, and the waste body can be isolated and left to degrade, or is sealed off from the environment. On top of the geomembrane, we can see this composite material that's placed on top. So if you refer back to the previous matrix, the geocomposites serving that drainage function, and essentially here, the geocomposite will collect rainwater that penetrates through this capping soil. So on top of the composite, we can see capping soils being spread. This could be 0.5 meter to 1 meter of soils, but this will allow rainwater to penetrate through, and the drainage composite underneath will efficiently drain the water out of the system. And what that does is it reduces the amount of hydraulic head that acts on that geomembrane liner beneath the geocomposite material. So the more we can reduce the hydraulic head on this impermeable liner, if there were to be any imperfections or holes in that liner, the leakage rates will be low, because the hydraulic head is the driving force that drives leakage through any defects. This is an example of a geo-web, which is essentially a geocell. And again, this is about confinement, and these pockets, these cells come in various depths, so 75 millimeters, 150 millimeters, 200 millimeters in depth. And these cells are then infilled with granular material. So it could be a sand material, a soil, an aggregate. You can place these cells on slopes. We can use anchors and tendons to hold them on slopes and then infill them to hold material on much steeper inclined slopes. Or we can use them for bearing capacity improvement as well. So if we was to lay these down on a road or a haul road, we can infill these with aggregates, and this allows for a much larger overburden stress to act on the subgrade and improve bearing capacity by utilizing these types of material. Another example of stabilisation here. So we can see a geogrid that's been deployed on a compacted subgrade, and then we have this plant pushing the granular material above. So essentially, the way that these geogrids work is that the granular aggregates will interlock in between these apertures. So if you look at these triangles on this triax geogrid here from Tensar, the angular material, the rocks, will partially penetrate through these apertures, and by locking in with the geogrid, again, when an overburden stress is placed on that system, because the aggregates are locked in, it prevents that lateral spread of aggregates, and hence we can either use less of a thickness of this granular material, or we can improve the bearing capacity, or a combination of both. Okay, so that gives you a few examples of geosynthetics and the uses and the functions. So if we talk about the United Nations Sustainable Development Goals and how they link to geosynthetics, there's a very good paper by Natalie Tooze, and I've given a reference there, and there's a reference at the end of this presentation as well. But this gives a really insightful view on how geosynthetics can actually link to all 17 of the United Nations Sustainable Development Goals. So I would encourage everybody to either have a look at that paper or visit the International Geosynthetic Society website on the sustainability section, and there's a video of the lecture on there, and it's a fantastic lecture on geosynthetics and how they can help achieve all 17 of the United Nations Sustainable Development Goals. I'm going to focus on a few of those with the geosynthetic types and materials that Geofabrics can supply to mining projects. So we'll look at the 4 Sustainable Development Goals that I've got on the page here. We've got Sustainable Development Goal 3, good health and well-being. Number 6, clean water and sanitation. Number 14, life below water. And number 15, life on land. So various mining processes can impact on the environment, and by utilizing geosynthetics, we can limit and improve the environmental protection. So there's a number of applications here: mine waste storage, just as some examples. Cell lining systems and capping can fall in that storage category. Heap leaching facilities, tailings dams, evaporation ponds. All of these have significant chemistry involved and stresses involved that can impact on the environment. So, we can look at these various processes, and these could lead to acid and metalliferous drainage, elevated sulfate salinities, elevated sulfate and chloride concentrations. There can be some radioactivity involved in these processes from extracting these minerals out of the ground. We can be producing sulfuric acid solutions during processing, hypersalinity in coal seam gas processing, for example. We can employ reverse osmosis to treat produced water, and an outcome of that can be a hypersaline solution that's then stored in these evaporative ponds. High alkalinity leachates are common in bauxite refinery processes. Elevated sodium concentrations, elevated metal concentrations, cyanides and hydroxides are all things, and some of the examples that we see when we're looking at employing geosynthetic solutions to protect the environment. Okay, so I'm going to look at a few of the geosynthetic types now and delve into what they are and how they can assist in environmental protection. So the first geosynthetic I'm going to discuss is a material that Geofabrics manufacture here in Queensland, and this is a geosynthetic clay liner, or a geosynthetic barrier. Clay is a number of ways how they're abbreviated. So an Elka seal is an example of this, which Geofabrics manufacture. So GCL is a manufactured liquid or gas barrier, and it's comprised of a sodium bentonite clay, and it's sandwiched between 2 synthetic geotextiles. The whole sandwich is needle punched together and then firmly locked on the underneath, and that provides internal reinforcement to that clay layer. So you can see a cross section here on the right. This whole layer would maybe be about 8 millimeters in thickness. This bentonite layer will be maybe 6 5 to 6 millimeters in thickness, and it's a very specific type of clay. It's got a high montmorillinite content. And when we manufacture these GCLs, the clay is placed in this system in a dry state. So the bentonite is mined here in Queensland, and it's milled, and we receive the bentonite in a powdered form at approximately 10 to 12% moisture content. We then scatter that onto the carrier geotextile that carries the bentonite, and it's not until the geosynthetic is completed and the bentonite is then in a hydrated state when it's installed in situ, that clay can swell and expand and form a hydraulic seal. So when that bentonite becomes hydrated, when it uptakes moisture from its surroundings, it has a very low permeability. And we can measure that level of permeability, and what that level of permeability is depending on the chemistry that interacts with that liner. And I've got an example next, as I say. So the GCLs, they are the manufactured rolls, and they're typically 4.7 meters wide, and they can be up to 80 meters in length that are formed on a roll. So each one of these rolls, it could be a ton and a half in weight per roll. And when we roll those out, as you saw in some of the images earlier, we overlap them to create that hydraulic seal. So typical applications for GCLs, that include basal liners, caps, bunds, ponds, and water storage. GCLs can be used, or they are often used as composite liners. So the one element within a lining system. So it could be a secondary barrier where a geomembrane is placed above it. So if there's any defects in the geomembrane above, the GCL can then capture any leakages that occur there. Or depending on the chemistry or the risk to the site, GCLs can also be used as a primary liner, so a sole liner for lining a water storage pond, for example. So in order to quantify the level of permeability of GCLs, so there's many different ways we can construct GCLs. There's different types of GCLs that we can construct for the slopes, and a different type of GCL that we would use on a base. We can change the level of needle punching. We can change the amount of clay. We can modify the clay with polymers, all depending on the chemistry that's going to interact with the GCL. And this, the way we measure that's in a triaxial permeability cell, and there's an example of that on the right there. So what we do is we hydrate and we permeate the GCL with the chemistry, the liquid that it's going to interact with, because we want to know how it's going to perform over the long term. And there's a few examples of that here. So this is a hydraulic conductivity chart, and it shows, how long we conduct these tests for to demonstrate long-term performance with these various liquids. So there's examples of hyperalkaline liquids, calcium chlorides, saline sodic brines, sodium hydroxides, steep gas condensates, diesels, and even seawater. So a lot of these types of chemistries and liquids, you wouldn't achieve this low level of hydraulic conductivity with some standard bentonites. We can specifically modify the bentonites with certain polymers to be able to protect the clay structure when they're exposed to these liquors or leachates, and then we can measure that in the laboratory to confirm long-term performance. Another example, so we have the capability here at our factory in Queensland to create what we call a hybrid GCL, and one example of that is SorbSeal. So we developed this in the R&D laboratory to attenuate PFAS impacted liquids, and it's just an example of some of the testing we've done here. So we for this particular case, we can blend in a certain percentage of activated powdered carbon into the bentonite mixture, and we can place that inside of a GCL, and by using a specific type of activated carbon, it allows us to capture some of these longer chain PFAS contaminants, and again, something that we can measure in the laboratory and something that we can formulate adjusting to the chemistry that's expected. So we can measure the chemistry of the intended liquid that's going to pass through this type of liner, this type of barrier, and we can measure the effluent that comes through the material. And by looking at the chemistry of the effluents, we can see the effectiveness of the adsorbance of the blend that we're placing this hybrid type of GCL. And the whole idea is that by slightly modifying the bentonite with these different additives, we want to keep the GCL construction the same. So the physical and the mechanical properties and the hydraulic properties remain as a traditional GCL, with the added benefit of being able to absorb some emerging contaminants of concern. So this graph on the left there, this demonstrates that we still achieve a low level of hydraulic conductivity with the leachate in question, as well as being able to have some absorptive properties and essentially act as a filter to some of these contaminants. Okay, that's geosynthetic clay liner. So moving on to the next slide, I'm now going to talk about geomembranes. So again, another barrier. We talk about barriers because they're important in terms of environmental protection. So geomembranes, there's a large range of geomembrane types, and they're either generally classified as either thermoplastic or thermoset. So there's a table there on the right. It details thermoplastic geomembranes, thermoset geomembranes, and then combinations of. So you can see that thermoplastic geomembranes include HDPs, LLDPs, flexible polypropylenes, PVCs, EIAs, TPUs, and then on the other end of the scale, you've got thermoset with a range of rubbers and then combinations of. So that can include your bituminous type geomembranes and some others there. So geomembranes, again, these are flexible polymeric sheets, and again, they're used as liquid and or vapor barriers. And polymeric and elastomeric geomembranes, they're designed as relatively impermeable liners, and they're used in a wide range of containment applications. So these geomembranes are typically a primary barrier in a containment system or a capping system, and they are the first line of defense in protecting the environment from contaminants. So key thing to note is with good installation and good protection, membranes can be foreseen as impermeable, but we need to keep in mind that during installation, these materials can be damaged, and with holes that are imposed on these liners, that can impact on the permeability, because you're no longer measuring that diffusion through these type of membranes. You're actually measuring liquid or gas flow through a hole. Just to give you an idea of the market of geomembranes, there's a section here in the bottom right, and this outlines the different membrane types globally and what the sort of proportions are used of each type. So you can see that your polyethylenes, HDPs and LLDPs, they probably account for 65, maybe 70% of the global market of geomembranes, with PVCs coming in second. PVCs are used a lot in tunneling, for lining tunnels, followed by some of the other membrane types. So because polyethylenes account for such a large proportion of the market, I'm going to focus a little bit more on polyethylenes just for this presentation. So as we can see, polyethylenes are the most widely used group of polymer in the geomembrane category, and mainly we talk about HDPE, which is high density polyethylene, and LLDPE, which is linear low density polyethylene. They're the two main subgroups, and they're defined by their density. So the cutoff there is that 0.940 grams per cubic centimeter. So anything less than 0.940 would be classified as a low density polyethylene, and anything higher than 0.940 would be classified as a high density polyethylene. So geomembranes, they are polyethylene geomembranes. They're formulated, so it includes a polyethylene base resin and that accounts for the majority of the membrane, 90% plus. And then to that, there are additives added to that. So that includes carbon black, which gives you HDPE's traditional black color, or titanium dioxide. So we've seen some examples of white geomembrane. So it's the titanium dioxide, the pigment that gives the membrane its white color. And then to that, there are stabilizers and antioxidants added to that as well. So that's what give these geomembranes the longevity. So the specific types and amounts of stabilizers and antioxidants contribute to the longevity of the polyethylene. So these types of membranes, they have different finishes to them. They can either be smooth on either side, they can be textured on either side, and they can have texture on one side and smooth on another. So it all just depends on the application and on how they are used. On slopes, we typically see textured membranes. On the base, on flat surfaces, we see smooth membranes. If we don't want to inflict any tension in the membrane, which is usually the case, we would use monotextured type membranes on slope. So you have the textured surface that would grip onto the subgrade or material below, and then above you would have smooth, which allows for a slip plane so that you don't get any tension generated in the geomembrane. So these polyethylene geomembranes, they can be monolithic or they can be co-extruded. So you can have the example whereby you have just solid black HDPE, or what we see more and more on the market now are co-extruded geomembranes. So that can include two or more layers of different polymer. So an example there could be a white and black geomembrane. So we can have 50% of the membrane thickness, which would be white, and 50% which would be black on the base. And those can be beneficial in applications where we want to reduce heat. So by utilizing a white geomembrane, it doesn't absorb as much heat, it doesn't wrinkle as much, and it can reduce temperatures on the underside of the liner. And an important thing to make note of here is that not all HDPE and LLDPEs are the same. So there's those various different elements that are used to formulate these liners. So there's many different base resins available globally. There's many different stabilizer and antioxidant packages, and the concentrations and levels of those result in the fact that not all HDPEs or LLDPEs can be classified as the same, and they certainly don't perform the same as well. There's a chemical resistance chart here at the bottom, and this just indicates, quick reference as to chemical resistance of HDPE. So HDPE is very good in concentrated acids, alcohols, bases. Excellent resistance observed there, and then we can look at the other end of the scale with limited resistance or moderate attack with hydrocarbons or oxidizing agents. So essentially, they're attacking the oxidizing agents can attack the stabilization packages, and it's those stabilizers and antioxidants that give these geomembranes the longevity. So the reason we use HDPE for containment is displayed by this chart here on the right. So as you increase polyethylene density, its crystallinity increases, and as you increase crystallinity, you get an increase in chemical resistance. So because HDPE is very crystalline, it's got really good chemical resistance for a broad range of chemicals. The only impact on the fact that you increase in crystallinity is that it makes the HDPE susceptible to stress cracking. So ultimately, stress cracking is where the membrane can fail and crack under low stresses. So that's what we can quantify and again measure by laboratory testing to look at the durability of these types of liners. So there's a number of durability parameters for geomembranes. So that includes oxidative induction, stress crack resistance, oven aging, and UV resistance. So we can again measure all these in laboratory. There's a chart here on the right that details the stabilizers and the range at which over these operate. So there's different stabilisation packages that goes into these membranes that operate over different temperature ranges. So you have processing stabilizers and long-term stabilizers, these phenols and phosphates that are used to protect the geomembrane based resin at higher temperatures. So during production, when the membrane's in a molten state, but then also when the membrane gets on site, it needs to be welded together at the seams. And those welds are obviously made at high temperatures where we're melting two sheets together. So there needs to be some level of stabilization and protection of the resin at those elevated temperatures. And then when we look at longer term performance, there are these packages that include thiosynergists and hindered amines, and these can protect the geomembrane both in an exposed state. So if we're looking at an exposed geomembrane that is going to be exposed to ultraviolet rays, we need to protect the polymer from ultraviolet degradation, and it's these hindered amine stabilizers that are used to protect the membrane when they're exposed to UV light. Performance testing. So we do performance testing on these types of membranes to confirm and to predict service life of these membranes with certain chemistries and at certain temperatures. So these membranes can be exposed to a range of chemistries that we discussed earlier, but also these chemistries might be operating at elevated temperatures as well. So we need to be sure that that stabilization package that we include in these membrane types is sufficient to be able to protect that membrane, because essentially what happens is the antioxidants and stabilizers that are included within these membranes, it's those formulations that are protecting that base resin, and it's the service life of those formulations that we're predicting these tests. And what happens is once all those antioxidants have been consumed, is that then exposes the base resin, and eventually the resin will become susceptible to stress cracking. It becomes brittle, and then when we get stress cracking, that's essentially when you lose the impermeability of the lining system, because it's fractured and it's failed, and it's got fractures in there. So to be able to predict that lifetime, we do a series of immersion testings, and it can include shorter screening, but then longer term testing as well. So we take the chemistry that the material is going to be exposed to, we take the liquid or the leachate, the liquor, we expose the membrane to that liquid at elevated temperatures. So because we expose the membranes to these liquids at the elevated temperatures, the increase in temperature accelerates that chemical interaction and degradation. So as a rule of thumb, you can consider that for every 10 degrees Celsius increase in exposure, you can expect something on the order of 2 times the rate of degradation to occur. So when we do these Arrhenius tests or immersion testing, we conduct the testing at 65, 75, 85 degrees Celsius, because we want to measure the degradation quickly and in a reasonable time frame. And then by measuring the degradation at those elevated temperatures, we can then use a regression type analysis to say, in situ at an operating temperature of say 20 or 30 degrees Celsius, we can predict how many years service life we will get from the membrane. So as the test progresses and the exposure of these membranes to these liquids occurs, we can periodically take samples, we can measure the levels of antioxidants, we can measure the tensile stresses, we can measure what's happening to the material as time progresses, and that allows us to make those predictions. Okay, so geotextiles, and with geotextiles, as I mentioned earlier, there's a number of functions that these geotextiles can occur and that they can use. So the main polymer types for geotextiles, the polyesters and polypropylenes. that we typically use, and I described earlier there's different construction methodologies. We can have woven, knitted, non-woven, and then subgroups on from the non-wovens. We can have needle punch, spun bond, heat set, staple fiber, continuous filament. It's important to note that all these different types of methodologies can impact on the use of materials. There's testing again that we can conduct to look at the level of cushioning that these materials can provide. So we can do cushion testing analysis. We can look at the levels of strain these cushions can improve upon to protect geomembranes from high levels of strain. Geotubes, again, I mentioned geotubes earlier, and I talked about geotubes, and we can use geotubes to contain slurries and waste materials. Essentially, we pump these geotubes with wet slurries and slurries, and that allows us to contain the slurries and quickly take the water out of the system. We can reuse the water. There's a number of benefits with geotubes, so we can process high volumes over a smaller footprint. We can reuse the water that comes out of them. We have a low CO2 footprint. We can prevent rehydration of the tailings, for example, that are pumped into these. It mitigates airborne dust issues, plus some other benefits. Rolled erosion control products. Again, we can use these to prevent or assist in the erosion of subgrade soils. So again, it's all about dissipation of energy and preventing erosion of soils on slopes with erosion control products. I'm going to quickly go through some slides here based on life cycle assessments. So we can do life cycle assessments on these geosynthetic materials, and those life cycle assessments can be then verified externally into environmental product declarations, and that allows for calculations of carbon footprint. So there's various stages and boundaries for a life cycle assessment. So cradle to gate, cradle to site, cradle to the end of construction, and then eventually cradle to grave. And there's a GRI white paper, there's a reference at the end of this, and GRI white paper 41, it gives some examples of traditional methods versus geosynthetic methods, and on the whole, the conclusion is, there can be up to 65% or more carbon savings by utilizing geosynthetics compared to traditional methods. Here's a few examples. So if we were to use a tensile geogrid to stabilize a haul road, in a non-stabilized example, we're using 970 millimeters of aggregate. By incorporating 2 layers of stabilization geogrid, we can reduce that layer to 455 millimeters. So we're using less struts, and there's less energy being used in being able to construct this haul road. The example here, over a 5,000 square meter footprint, it can be up to 41 tons of CO2 saved when we look at a traditional method compared to a geogrid stabilized method. So that's significant. Geotube tailings dewatering, there's an example here of mechanical dewatering with a belt filter press compared to geochobe. I can share these with you in detail if you contact me, but essentially the geotube has in this particular example has resulted in 153 less tons of CO2 compared to a mechanical dewatering belt. Concrete canvas, which is a GCCM, it's a rolled material that's embedded with cement. We use these for various applications, but this example here is lining a drainage trench. So if we compare a traditional concrete lined trench, 150 millimeters thick with a 20 megapascal concrete, and then compare that to a concrete canvas lined dam, you can see in this particular example, over a 500 meter length of channel, there's actually 63% lower carbon that's embedded within that footprint compared to a traditional methodology. This example is an example of a compacted clay layer to assist with hydraulic performance. So 1 meter of compacted clay versus an Elca-sealed GCL composite barrier. And here I'm just looking at truckload. So there's a whole other range of assessments to do in terms of construction and compaction of the clay, but just in terms of transport, over a 1 hectare site, if we consider that the borrow pit is 10 kilometers away and the Geofabrics plant is 1,000 kilometers away, you know, to transport that amount of clay to the site, we need 470 42.5 ton trucks to transport that clay to construct that barrier over 1 hectare, whereas you know, for the equivalent area, we just need 2 trucks of GCL. So that's significant in terms of CO2 footprint just in transport alone. So just to finish, I've just got a few slides about Geofabrics and you know, why choose local. So Geofabrics, we're the only geotextile and GCL manufacturer in Australia, and our products and solutions are made and tested to withstand local conditions. We've got branches throughout the country, and a key here is that we're local manufacturers. So we employ over 100 production staff over 2 sites in Queensland and New South Wales. We contribute over 10 million per year into regional communities, and we actually support over 1,000 active suppliers in regional Australia. A little bit of a timeline in terms of you know, the Geofabrics business, established in 1978. So we've been making Bidham geotextiles since 1987. Forward to you know, just a few years ago, we started incorporating recycled material into Bidham geotextiles. So we're taking waste polyester and incorporating that into geotextiles. 2022, so that period, we've diverted 40 million recycled bottles and reused those in manufacturing of geotextiles, diverting all that waste to landfill. And looking forwards, we're now looking at reducing emissions. So at one of our plants in Albury, you know, there's up to 6,000 tons of carbon savings per year, because we're going to be installing solar power there in the manufacturing process, upgrade air compressors to be more efficient. That's an additional 420 tons of CO2 savings per year. So this covers our scope 1 and 2 predictions. And again, at our manufacturing plant in Queensland, similar outcomes. We're looking at, we are installing solar panel to assist with using green energy in production. We have processes to recycle bentonite that again has significant savings in terms of waste and CO2 resultant from that. And again, just highlighting the fact we're Australian made with recycled materials. So we source polyester and HDPE to make geotextiles and drainage pipe to support the circular economy. So further to that, we have what's called the Geofabrics Academy. So we have dedicated sections within this academy that have a focus on geosynthetics and their use. We have partnerships with universities, and I encourage you to visit our website to look at the further information that's available on the Geofabrics Academy. Some references from today's presentation, so please have a look at those, as I've mentioned them throughout the slides. And that's the end of this presentation. So I welcome any questions, and thank you very much.
Thank you, Ryan. That was terrific. The yes, the environmental, social, and governance qualifications of Geofabrics and the application of your products is significant. So thank you very much for sharing that.
No problem.
There's one question there, and I was asked a bit earlier on shelf life of some of your products, but I think you addressed it later in your presentation with some of the lab work that's then.
Yeah. So when the question, how long will the Geosynthetics products last when in place and buried? You know, it essentially in a neutral environment. So different polymers degrade in different ways. Polyesters are subject to hydrolysis, and polypropylenes are more susceptible to oxidation. It ultimately depends on the quality of the material that's used, the additives that are used to protect the polymers from breaking down. But in a neutral environment, at service temperatures less than 25 degrees Celsius, buried products will last in excess of 100 years, 200 years, 300 years. It all comes down to temperature and chemistry and stress. So, you know, if we start looking at higher pH solutions or higher temperatures, you know, that can accelerate. But essentially, buried in a neutral environment, these materials can be in situ for hundreds of years. Okay. So, yeah, I hope that that answers
Thank
that
you.
question.
We've run a little bit over time, so we might wrap it up there. And big thank you to Ryan and the team of Geofabrics for sharing your expertise and value in your products today. The webinar will be circulated as an email link to all attendees, and we'll be uploading it onto Osmine's YouTube platform. Any further or specific questions you want to channel to Ryan, please contact us here at Osmine and we can put you in touch directly. There was an email address on one of those later slides, but we can connect people through. Thank you to all those that have attended, and look forward to welcome you to the next Osmine webinar series, and stay safe. Thanks for attendance.